Hey everyone. So today we're going to be looking at mass spectroscopy. We're specifically going to be looking at spec for elements. So let's go ahead and get into this. So really quickly, we need to review slash define a few terms and make sure we're comfortable with it. And the first one is going to be an isotope. Now, just to remind you, an isotope is going to be an atom of the same element with different numbers of neutrons. Neutrons, remember, are the neutral subatomic particle that exists in the nucleus. The other subatomic particle that is in the nucleus are protons. The number of protons cannot change for a given element. The only thing that can change in the nucleus is the number of neutrons. With that being said, that means that different isotopes, different stable isotopes of an element, will have different masses. A good example of some isotopes that exist for hydrogen are protium, deuterium, and tritium. These are just like the common names for these three isotopes of hydrogen. Notice that in each one of these examples, the hydrogen isotope has one proton, and that's because a proton is how we define the atom. But protium has no neutrons, it only has a single proton. Deuterium has a proton and a neutron, and tritium has one proton and two neutrons. So these are isotopes of each other, and the reason that is because they have different numbers of neutrons within the nucleus. So let's go ahead and talk about average atomic mass. Average atomic mass is the number that is quantitatively equivalent to the molar mass. It's the number that is on the bottom of the periodic table. And the example we're going to be looking at is carbon. Carbon's average atomic mass, or molar mass, is 12.01 AMU, or 12.01 grams per mole, respectively. So average atomic mass is the weighted average of the naturally occurring isotopes of the element. So for carbon, there are two naturally occurring isotopes, carbon-12 and carbon-13. Carbon-12 is kind of special. The reason that it's special is because it has an exact mass. Carbon's mass is exactly 12 atomic mass units. So that's why it doesn't have any decimals following it when we go ahead and look at the mass of that isotope. Carbon-13, however, is not exact. The mass is 13.003355 AMU. And what I want you guys to kind of think about here is, okay, there are two isotopes that exist in nature for carbon, but the average atomic mass for carbon is 12.0107. So we're thinking about these weighted averages here. What do I have more of? Do I have more of this carbon-12 or more of the carbon-13? And that's what we're going to kind of look at here. Like, which one of these would be better represented? I'll give you a second to think about it. Hopefully you see that 12.0107 is much closer to 12 than it is 13. And so therefore we can make the correct assumption that most of the carbon that exists in nature is going to be carbon-12. Rather, 99% of it is carbon-12 and about 1% is carbon-13. And that's why it's so heavily weighted towards the carbon-12 mass. So there's this a formula that I want you guys to kind of keep on the back of your mind. It's an informal formula, and the reason I say informal is because it's not given to you on the AP Chem formula sheet. It is as follows. The average atomic mass is equal to the mass of the specific isotope times its abundance plus the mass of the specific isotopes times its abundance plus et cetera, et cetera, et cetera. So you do this for however many naturally occurring isotopes that exist in nature. So for example, if we were going to be doing carbons, the average atomic mass for carbon would be, so the mass of carbon-12 is exactly 12 times 99%, which we know percentages have to be listed in decimal form, plus 13.003355 times 1%, which would be 0.01. So this comes out to be roughly 12.0107 blah, 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 AMU. All right, cool. So let's actually get into some more specific examples here. Let's go ahead and look at and calculate the average atomic mass for potassium. I believe, yeah. Okay, so there are three stable isotopes for potassium: 39, 40, and 41. And as we could see, most of potassium is potassium 39. Generally, most of the isotopes that exist for a specific element are heavily weighted around one of the isotopes. That's not the case for all isotopes. For example, chlorine has a pretty even split between the two isotopes that exist for it. But potassium 39 looks like it's going to be 93.26%. Potassium 40 is going to be very small percent, 0.0117%. And potassium 41 is going to be about 6%, 6.73. So when we're calculating this, I just want to remind everyone that when we look at this, always scoot your decimal place over twice. So 1, 2, 1, 2, and 1, 2. And our math is going to end up looking like this, where the average atomic mass is the mass of the first isotope times its abundance, plus the mass of the second isotope times its abundance, plus the mass of the third isotope times its abundance. And we go ahead and calculate this out, and you get 39.09 atomic mass units, which is nice because you can go ahead and check this by looking at the periodic table. And the average atomic mass for potassium is 39.09 or 39.1, depending on the periodic table you're looking at. So cool, that one is a go. We're good with that. So why do we talk about isotopes? Well, we need to understand that mass spectrometers are devices that allow for us to determine the relative abundance of these isotopes that exist in nature. So for example, if I were to take a sample of potassium rock that I found on a walk out in nature, which I wouldn't be able to do because potassium is highly reactive, but let's say I found a rock of potassium. I could put it in my mass spectrometer, and it could tell me the relative abundance of each isotope that existed in that rock. This functionality is not important for you to know. You just need to know that this device does that. So here is some mass spectrometry data. It looks like there are 1, 2, 3, 4, 5 different isotopes that exist for this isotope. And what we're going to go ahead and do is we're going to go ahead and calculate we're going to go ahead and determine the identity of this isotope. And the way we're going to do this is by determining the average atomic mass. That is an intensive property, meaning that we can go ahead and do this because the average atomic mass for an isotope is always the same, or for an atom is always the same. So just to make our lives easier, I went ahead and listed all of the 5 isotopes that exist with their percentages. It's not perfect, but it's close enough. 90 times 51 plus 91 times 11 plus 92 times 17 plus 94 times 17 plus 96 times 0.04. And it looks like I didn't go ahead and do this. So why don't we go ahead and punch this out and see what we get. So 90 times 0.51 plus 91 times 0.11 plus 92 times 0.17 plus 94 times 0.17 plus 96 times 0.04. So it looks like the average atomic mass for this chemical is going to be roughly 91.37 AMU. So I can go ahead and pull up a periodic table. And find out what substance, what chemical has the average atomic mass of roughly 91.17. Of course, you need to find a periodic table that has masses on it. It's going to probably be, let's see here. Finding the tables. Is it time to sing, I guess? There we go. That's a good one. Looks like it's going to be zirconium. It's closest to ZR zirconium, which has a molar mass of 91.22. And because I so haphazardly figured out the percentages here, we're going to get a little bit of a range from the true value. And that's fine. That's absolutely okay. Remember, estimation is part of the game when it comes to taking measurements in chemistry. All right, so let's go ahead and do a little bit more straightforward one. Determine the average atomic mass. This was a 3-to-1 ratio. So one way we can go ahead and do this would be to determine the average atomic mass, or excuse me, is to determine the ratio here, which in this case is about 3/4, right, for 35. And 1/4 for 37. We do that math and we find out it has an average atomic mass of 35.5, which would identify as chlorine. All right, so last but not least, and I want you guys to do this on your own. I want you to create a mass spec graph given this following data. Please make sure you appropriately label your graph and identify the average atomic mass of neon. And compare it to the periodic table, see if you get fairly close. We'll talk about this graph in class later. All right, y'all, have a good day.